Hi, my name is Nick Arnasti. I'm a professor at the University of Minnesota, and I'm going to tell you a little bit about some work that I did with Felipe Simon, who was a student here at Minnesota, is now a professor at the University of Chile. So as a starting point, I'm going to tell you about a classic matching problem, which is maximum weight matching. So in this problem, we have a set of vertices, we have edges connecting them. Our goal is to match vertices in pairs, and each edge earns us some reward, which is the weight of that edge. And our goal is to find a matching with maximum weight. So in this example, for example, we could get a reward of 12 by matching A with C and B with D. But it turns out we can do better than that. We can actually do 15, for example, by matching A with B and C with D. Or there's another way we could get 15, which is this matching here in black. But either way, 15 is the maximum weight matching of this graph. And so you might wonder, is there an efficient way to solve this in general for large graphs? And the answer is yes, we've had algorithms to do that since about the 1960s. So that's a very classic matching problem. But that's a matching problem where we know all of the vertices up front, and we have to make one set of decisions, right? One decision once. The setting I'm going to be studying today, or telling you about today, is one where instead the vertices are arriving and departing over time. So they're not all present in the market at the same time. And we need to make decisions in real time about whom to match with whom. So here's the model we're going to be studying more concretely. Has four components. So first, we have a finite set of types. So each arriving vertex is going to belong to one of these types. Second, for each type, it arrives according to a Poisson process. And we let lambda I be the arrival rate of agents of type I. Okay. Now, agents that arrive in the system are going to stay around for a limited amount of time. In particular, we assume that that time is exponentially distributed, and that exponential distribution has parameter mu I. So think of mu I as being like the urgency of this type. If mu is very large, that means the type disappears very quickly. It's very impatient. If mu is small, that means they're going to wait a long time. And finally, we have rewards for matching any pair of agents. And so these are encoded through a matrix, R, and Rij tells you what is the reward for matching type I with type J. Okay, so that's the model. It's a foundational model of dynamic matching. And it has many potential applications. So, for example, you could imagine playing online chess, right? I like to play online chess. When I log into the server, I am one of many people who might be logged in at the moment requesting a game. So let's imagine that the server sees these four people. And in this setting, we could think of the type as capturing the ELO score, essentially a measure of the skill of the players. And we could imagine that the goal is to match players of similar skill. So the reward is higher the closer the two players are in skill. And so now the server has to decide, for example, which matches should I do now? Or should I wait, for example, like maybe I don't want to match this 1600 player with this 1200 player, and instead I'm going to wait to see if another player who's closer to one of them in skill shows up, and so that I can do a better matching. But of course, if I wait, there's some risk that these players are going to get impatient and just log off and leave the system. Okay, another potential application is organ allocation. So in this framing, we can think of the types as capturing both patients and organs. So imagine that these are all patients who need an organ. And the type also can encode information about the patients or organs. So for example, where they're located, the age of the patient, the blood type of the patient, and so on. And for any pair of types, the reward matrix tells us how valuable is it to match them. And so in particular, in this application, we would actually have a bipartite graph where any valuable match is matching an organ to a patient, not two patients together, not two organs together. And then a second feature for this application is that the departure rate for organs is very, very high, right? So I might be able to tell a patient, hey, wait around until next week. But for an organ, I have to basically match it immediately or not at all. So these are just two potential applications of this model. We're not really focused so much on the applications as we are on understanding this foundational model. But I do think it has many applications in practice. So in this model, our goal is, given the arrival rates, the departure rates, and the reward matrix, to come up with a policy that does well. And in order to say what we mean by does well, we need to have some sort of benchmark of performance of like what is good. And so our benchmark is what we call the omniscient algorithm. And so I want you to think of this as follows. So suppose we're interested in some finite time window, say t equals 10. And during this time, um, it turns out 5 agents were going to arrive. Now, we're going to look at what we could do if we had perfect information about all of the arrivals and departures that are going to happen in this window. So in particular, suppose that we knew that these agents were going to remain in the system for time periods given by these brackets. Now from this, which matches can we actually form? Well, in order to match, say, A to B, we need it to be the case that they're both present in the system at the same time. Right? So we're going to draw edges indicating which matches we can make. So for example, A overlaps with B, A overlaps with C, so we're going to have edges there. But notice that A leaves before D arrives. And so there's not going to be any edge between A and D. So we end up getting these edges that indicate who we can match to whom. And once we have those edges drawn, we can sort of forget about the details of when exactly everyone arrived and just focus on this graph. But now we need to add edge weights. So in this example, think of the shapes as encoding the type of each agent. And over here we have rewards that say, matching a circle to a diamond is worth 5, matching a circle to a triangle is worth 4, and so on. So that allows us to put weights on this graph. And now our benchmark is going to be what performance could we achieve if we did the optimal matching in this graph. Right? So in this particular graph, we already know the optimal matching is going to have weight 15. We're going to convert that 15 to a per period reward. So remember, we were waiting 10 time periods. So that would be, in this case, a per period reward of 1.5. And we just look at essentially what is that reward rate that we could earn with perfect foresight. And we'll take the limit as this time horizon t goes to infinity. And that will be the benchmark that we're aiming to achieve is what if we had not only very good matching algorithms, but also perfect information about the future. Now, of course, we can't actually achieve this benchmark. So our goal is going to be to design an algorithm that gets some constant fraction of that benchmark. And we're not the first to study this model or this question. So in particular, there was a paper from Wine 2020 that showed that no matter what the instance is, no matter what your reward rates are, et cetera, you can always design an algorithm that gets at least 1/8 of this omniscient benchmark. Now, most subsequent work has actually focused on special cases of this problem with additional structure. So for example, you might assume that the instance is bipartite. Or going further, you might assume that it's what I'm calling a deceased donor instance, which is not only bipartite, but also one side of the market, the organs, departs immediately. So for that particular setting, it was shown just a couple of years ago that you could actually have an algorithm that achieves 39% of this omniscient benchmark. And if you're willing to make even stronger assumptions, namely that there's only one type of patient in the deceased donor instance, so there's one type of patient, there may be many types of organs, but the organs depart immediately. In that case, it was known that you can get a half of this omniscient benchmark. And this is really the state of the field. This is what was known before we started working on this. And so our main contribution is actually going to be to greatly expand the set of instances in which we know we can get a half of this omniscient benchmark. So in particular, our results are going to imply this 1/2 result that was already known, but expand it to a much larger set of instances. Now, being a little bit more precise, I'm actually going to give you 3 different theorems. And all of them basically say we can get a half under certain assumptions. So then looking at a graph like this, or at a picture like this, you might say, hey, if we have all these different conditions in which we know we can get a half, could we maybe get a half no matter what the instance is? The answer is I don't know for sure, but we suspect or hope that we can. And in particular, we identify an algorithm for any instance, regardless of whether our assumptions are satisfied or not. And we've tested a lot of instances, and we have yet to find one where our algorithm is worse than half of the omniscient. So we're sort of optimistic that maybe we've actually found an algorithm that is within a factor of a half or within a factor of two of this omniscient benchmark. But we've only been able to prove that in special cases. So what are these conditions? What are these assumptions we need in order to prove that our algorithm performs well? Here they are. There are three different theorems. So looking at the first one, the first case in which we know our algorithm works well is if all agent types have the same departure rate. Okay? Then we know that our algorithm is within a factor two of the omniscient benchmark. The second case that we know is if we have a bipartite structure and on each side of the market, the departure rates are the same. So it could be that we have patients and we have organs, and organs disappear very quickly, whereas patients stick around for longer. That's fine as long as all patients have the same mu and all organs have the same mu. Okay. And then the third theorem here, we're including really just to show that we don't necessarily think the assumption of homogeneous mu is required. So this is saying if we only have two types, then regardless of what the mu's are, our policy is going to achieve half of the omniscient benchmark. Okay, so these are our results. You might wonder, why am I obsessing over a half? Could we maybe aim to improve that one half further? And the answer is no, right? So it's actually well known that there's no algorithm that can guarantee more than half of this omniscient benchmark. In other words, there are some bad instances where no matter how clever you are, the fact that you don't have access to information about future arrivals and departures means that you can only do half as well as someone who does have access to that information. And the type of example that shows this is as follows. So imagine that we have two types, diamonds and circles. Diamonds are very rare. Circles are abundant. Unfortunately, we don't get any reward for matching circles with each other, right? So there's no point in matching circles. If we match a circle with a diamond, we get some reward, a modest reward, but it's not so great. And matching two diamonds together is amazing. So now if a diamond arrives, I'm forced to choose, do I wait and hope for another diamond? Or do I settle and match this diamond for a circle? Because of course, if I wait for another diamond, there's some chance that this diamond disappears and I get nothing from it. And so if you choose the parameter values carefully, you can make it so that those two strategies have about the same value, right? The waiting strategy versus the settling and matching with a circle strategy are about equally good. But if I had perfect foresight, I could identify exactly what are the cases where another diamond is going to show up in time. And for those cases, I'll have the diamond wait and I'll match them. And for all the remaining cases, I'll match the diamond to a circle. And so again, if you choose the parameters carefully, you can essentially get twice the reward from this omniscient strategy that you would from either of the strategies that doesn't have access to the information about the future. So all this is to say that at least if we're using this benchmark, one half is the best we can hope to achieve. So if I were to summarize kind of what I like about this work, why I'm excited to share it with you today, the first thing is that we get a tight competitive ratio of one half, right? So we're expanding the set of instances where we know for sure we can get a half, and we already know we can't go beyond that. But a second thing that I really like about this work is actually the policies that we develop. So I haven't told you anything about those yet. So far, I've just said there exists a policy, but in fact, we give the policy explicitly, and it has a very nice, simple structure that I'm going to show you on the next slide. And the third thing that I think is really unique and innovative about this work is actually we have a new proof technique that is quite different from the techniques used by other related literature. And so I'm going to tell you a little bit about that. Okay, but let's first go to point number two. What are the policies we're actually studying in this paper? Okay. We call them greedy policies, and essentially they're specified by, for each type, I'm going to say, which other types am I willing to match it to? And what is my preference or priority over those types? So for example, this table is going to encode one particular greedy example. It says, okay, anytime a circle arrives, I'm going to try to match it to a triangle. If there are no triangles waiting, I'm just going to let that circle wait and hopefully be matched in the future. When a triangle arrives, I'm going to try to match it to a diamond. If there are no diamonds waiting, I'm going to try to match it to a circle. If there are no circles waiting, then I'm going to have the triangle wait. And when a diamond arrives, similarly, I'll try to match it to a triangle. If not, I'll match it to a diamond, and otherwise I'll wait. So let's see how this particular greedy policy would play out in the example that we've already seen. Right? So remember, this was an example where the actual maximum possible reward was 15. How would this greedy policy do? Well, the first thing that happens is that agent A arrives, and I'm going to move myself over here. Okay, so agent A arrives, and there's no one to match to, so of course we just wait. Then B arrives, and if we look at the list for a diamond, we see that diamonds don't match with circles, so we don't form a match, we wait. Now agent C arrives. C is a triangle, and if we look at our list, triangles match with diamonds. So we make a BC match, which is worth 10, and now we have a reward of 10. Now the next thing that happens is that agent A disappears. Okay. Then agent D arrives, no one to match to, of course. Agent E arrives, and it's a circle, so we look at its list, and we see, oh, circles don't match with diamonds, so we wait. And then no more arrivals happen, so the process ends, and the total reward that we earn with this greedy policy is 10. So you might say, oh, it's really too bad that we didn't match that circle with that diamond. Maybe we should modify the policy to allow circles and diamonds to match. And maybe we should. The point is that it's not clear kind of what the best greedy policy is. That's going to depend on the parameters, of course, the rewards of like how valuable is a circle diamond match, but also the arrival and departure rates, right? So for example, if diamonds are very abundant, maybe then I'm fine doing circle diamond matches. But if diamonds are rare, I might want to save it to be able to match those diamonds, say, with triangles. So we're going to be studying greedy policies. And the question, in some sense, boils down to how do you design a good greedy policy, given your information about R, lambda, and mu? Okay, so that's the policy class that we're going to be focusing on. What about the proof strategy? I told you that we have a pretty innovative proof strategy. And so I'm going to try to explain it to you here. So this table shows numerical results from 100 randomly sampled instances. So we sampled lambda, we sampled mu, and we sampled R at random. And so the x-axis is really just like an index for these instances. There's no real structure encoded in the x-axis, but each vertical slice represents one instance. Okay. The green line shows you the performance of our omniscient benchmark on this instance. Okay. The blue line shows you the performance of our algorithm on this benchmark, on this instance. And then we want to compare, of course, blue to green, but it turns out analyzing theoretically what the value of the green line is a little bit tricky. So what we do is we come up with a linear program that is a relaxation of the optimization problem we're solving, and that's given by the black line here. So in this figure, we've normalized it so that the value of this linear programming relaxation is always equal to 1. Okay, and that's pretty standard. So if you look around the field and you see what techniques are being used, it's very common to say, I have a benchmark. My benchmark's a little complicated, so I'm going to use a relaxation that is more tractable or easier to analyze. And I'm going to compare against that relaxation, which I know has value that is weakly higher than the actual benchmark I started out with. So that's very, very common. Okay. What's really innovative about our approach is this orange line here. So this orange line is coming from a second linear program, a different linear program than we had in the black. And this linear program is really doing all of the work in our paper. So we use it for two things. One, we use the solution of this linear program to help us actually define our algorithm. So we solve this orange linear program, and from that solution, we identify an algorithm. But then second, and most interestingly, what we show is that this linear program gives a lower bound on the performance of the algorithm. In other words, the algorithm will always do better than the value of the linear program. And so this is quite new, I believe, the idea of using a linear program to give a lower bound for a maximization problem. And so then the final thing that we need to show, of course, is that the orange linear program is pretty good. And so in particular, that the orange linear program is always at least half of the black upper bound. And so our proof proceeds through this chain of inequalities here. Um, and they're all interesting in their own right. Um, Perhaps other than green greater than blue, that's pretty obvious. But I would say the really key innovation here is proposition one, which is showing that our algorithm is always earns a reward rate that's better than the value of the linear program in orange. So that's a little teaser of our paper and our results. Um, if you're interested in learning more about, for example, what is this new linear program that we do? How do we use the solution to that linear program to define our algorithm? And how do we show that that algorithm outperforms the linear program? I'll give you that information coming up in part 2.